So, welcome everybody. Thanks for attending that second virtual lecture of the week. In the first lecture, we focused on testing principle, like what was a test, how would it kind of like link to software development, how do we kickstart, like I have no idea what to test. Let's start with a small one. We also discussed that test a code. So basically everything that I can do with my code, I can also do it with my test, being defining maintainable test suite, thinking in terms of maintainability, readability, Boy Scout principle, broken window principle, all those kind of things, okay? So now that we have this, and again, you will practice during the tutorial in terms of writing your first test and thinking of your assignment from a test point of view, we should think of maybe a little bit more guidance on what to test. How, because there are so many options and there are so many points where to start with that it's pretty hard to be like, okay, what's my next step? Well, it's infinite. So which execution path should I select to be my next test? Hmm. There's no absolute answer to this, but there's some kind of like guidelines that we are gonna go through together. And first, before jumping into those guidelines, the first point is be like, what are we testing? Are we considering like our system as a white box so we can see the inside, or as a black box, like it's totally opaque and we have no idea what's happening inside. We're just sending data and getting output. When we'll clarify this, we'll go for section 2, which is related to BICEP. BICEP is an acronym that represents the different kind of things you should test when you're testing a module, being a class, being a method, being a package, being a product, being whatever you call a module, a unit. There are several things that you need to think of, like boundaries, for example, but invariant, conformance, all those kind of things. And if you bring all those letters together, you get BICEP. We don't have laws or equation in software engineering. We have lots of acronyms. So that's part of life. And the last acronym is something which is related to one specific thing. When we're testing, we'll test a lot what we call boundaries. Like I have an array and I want to test what's happening at the beginning, what's happening at the end, because usually what's happening in the middle, there's no out of memory, out of range exception, stuff like that, because well, we're in the middle, so we're safe. And to do this, there's another kind of acronym that guides you. So basically you can see it as checklist. So BICEP tells you what to test and correct tells you for boundary, which is a B of BICEP, what to test. So you can see it like as with zoom on all the things you need to think of when you're defining your tests. So first point is remember in software engineering, we're looking for trade-off and the only answer that makes sense is it depends. So it's very classical to take different point of view of a product. If I can take an external point of view, I can take an internal point of view, like knowing how the code is written versus not knowing how the code is written. And by jumping from one to the other, that can give me different perspective on what I can do with my software and also what I can test. Before jumping into this, something that you need to think of, and I will ask you to put the video on pause and just think about it, is why testing 100% of the product the most terrible idea you can ever have? Like really, literally, take a minute, put this in pause and think why reaching 100% testing is not a good idea because that looks amazing. If I'm 100% tested, that's maximal quality. So are we looking for poor quality software or what the deal here? So the question is first, what does 100% mean? Well, if you're testing 100%, it means that for each and every input of your system, you can predict each and every output of the system. Remember, a test is not a proof. It's I'm giving you a context. I know the expected answer, and I'm checking that the program produced the expected answer. So if I can do this for each and every input, and I know each and every output, I don't need a program to do that. The program is the test because I already know for each possible situation what is the outcome. So the system is useless. So basically the idea is here, if I already know everything, testing doesn't make any sense. So what we're looking for is not 100%, it's something which would be complete, okay? It means that, like I was saying for the boundary at the beginning, if we have an array of, I don't know, 1,000 elements, there is no need to write 1,000 tests, and there's no need to write hundreds of billions of tests that would represent all the permutation inside this 1,000 element array. That would be impossible. So what we're going to do is find what we call significant test cases. What happens if the array is null? What happen if we're at the beginning, we're at the end, we're in the middle? What happens if the array is sorted? You see, all of those represent states, significant elements from the business logic, from the business domain, the elements we're working with, and those are the ones we're going to test. So our expertise as software engineer is to first write the tests. Okay, that's what we did last week, and that's what you're going to do with the tutorial. And second, find the right test cases, find this significance, find among all the different possible stuff that one can test, what can be minimally done to test the most cases, to represent the most cases. And that's what you're going to practice in your second assignment, where you're in charge of defining what to test. So that's basically the kind of practice you're going to experience as part of the second assignment. So when we have those equivalence classes, well, we basically write one test or a couple maybe that are inside this equivalence class, and that's it. We're okay. We're not testing 100% because that is just simply not possible or would be useless. But we have identified something, took a design decision. This is a significant case that I want to be sure that my software can go through, and I have a test that demonstrates it. Again, not a proof. It just means like for the significant test case that I've identified and for those significant data that I'm using as a context, I have an answer that makes sense. Better than nothing. And this is kind of like a proof by accumulation approach. We're going to accumulate those test cases until we build our confidence into something that is sufficient for us to be like, okay, that should be fine. And as I said before, we can take 2 points of view. One point of view is the white box testing. Second point of view is the black box testing. White box testing, that's basically the same kind of approach that we had in the code quality lecture, where we're like, oh, I know the code. I have access to the code, so I can see it, I can manipulate it. So in this case, what we're usually doing is, for example, you see here, that's on the left-hand side, that's a code written in Python, but whatever. We're defining a function that takes x and y as input. If x greater than 0, write 1, else write 2. If y greater than 0, write 3, else write 4. This can actually be drawn as different execution state of my program. Okay, I'm starting in the state 1, which is basically just doing the test. Is x greater than 0 or not? If it's greater, I'm going to state 2, doing some stuff. If not, I'm going to state 3. I'm joining at step 4. Step 4 being my second test. Is y greater than 0? And if so, I'm going to 5, which is write 3. If not, I'm going to fix. Okay? So this gives us kind of like a data structure, which is a control flow. You will hear about tree and those kind of things, tree and graphs in 2 But basically what we have is a model of the code, okay? Those two things, the code on the left and the control flow graph on the right. They're basically two different representations of the same element, which are the program. And when we're doing white box testing, we have access to code, so we can define that model, and then we can look at it in terms of what are we testing. And there are several things that we can test. The first thing is the statement coverage. Okay, we have different statements. I have my right, I have my if, blah, blah, blah. You can imagine in your local global program. So if I'm focusing on working on the statement coverage, I want to write minimum test cases that will cover as many statements as possible. Okay, that will give me like a spread. Second kind of coverage I can focus on is the edge coverage. The edge coverage is looking at those, like how many, oh, sorry, that's a condition, but well, the edge is also the branches. So how many branch am I going through? And if I want to refine those edges, so kind of pass, I can be like, okay, what are all the possible conditions that I can go through? Okay. So with the edge, I can do like, that would be one coverage, and that would be another coverage. But if I go for condition coverage, I should be 1, 2, 4, 6, 1, 2, 4, 5, 1, 3, 4, 5, 1, 3, 4, 6. Okay, and kind of like each time zooming on and adding more constraint on all the elements I need to test. And that brings me to the pass coverage, which is we need to have each and every possible execution pass tested, which is actually the one that is impossible. Those statements, those coverage criteria, they're actually ranked from the easiest one to the impossible one. For that course, what we want you to do is to write test. You're discovering how it works. So 303, 3SO3, sorry, is a testing course. You will write, you will work on way broader comprehensive approach to testing. 2AA4, it's an introduction to software development. Just write some tests, find the right cases you want, and kind of like focus on getting your statements, maybe the edges, like just getting something which is, I have sufficient confidence that everything's fine. And then you'll see in 3SO3 all the theory, which is behind building the control flow, getting the coverage, computing the number of test cases you need to write to be able to cover all those kind of things. Those are kind of like mathematical stuff you will do in 3SO3. 2A4, very basic, just find the right stuff to test, write a test that does it, and that's it. And the coverage is something that can be computed. We can, because remember, when we execute a test, we're basically executing the program. So what's happening is that tools, like in Java, there's one tool which is named JaCoCo for Java code coverage. It's integrated in Maven in the classical test suite like JUnit. So nothing to do except just calling it. And this stuff will basically trace the instruction and the element that you've went through while you were testing. So you can basically just start the recording, run the test, end the recording, look where you were, and compute a percentage. And that's what you're seeing here. In this Sonar Q, which is code quality tool we discussed in the previous lecture, tells us that the code is kind of like tested for 32.7 coverage. And that gives us like 25% coverage on the 25 new lines that were sent. So that's pretty bad, actually. I mean that I've added like 25 lines of code in my system, and I've only tested 5. Nah, that doesn't sound reasonable. Doesn't mean that you need to get 100%, or there's also things that are like, if it's below 80, it's bad quality. You can't say that. It's always an it depends. I can get a 90% coverage with really crappy tests that just does nothing. I can have very small coverage, but very precise tests. And for the context of this course, this is what we're looking for. We want quality over quantity. Write tests that you need, write tests that helps you to be sure that your assignment is doing the stuff it's supposed to do, and that will be perfect. Don't try to do everything and just sprinkle some very shallow tests just to get 100% coverage and be like, hey, stamped, that's fine, my tests are good. That's not the point. That's absolutely not the point. And the important things here is that that tool actually reflects really well the definition of SoftEng by Google, which is programming integrated over time. And you see here, this blue shade is how the test coverage evolved among time. So you can basically see that, oh, that was high, and then bam, something happened, and then that went high again. Maybe someone had remorse or regrets, and then that goes down again. And this is kind of like a seesaw working like this. Usually what you observe, so this is not a real project, it's just a toy to show you like how it works. But usually what you should look for is kind of like a ramp up curve, where at the beginning there's not that many code and there's not that many tests, fine. And then you write the code, you write the test, you write the code, you write the test. You remember that duality that we need to do both. And then the stuff just slowly accumulates. That's something that you really need to do over time. Definition of software engineering. So you write your code, do nothing, no testing, and then start writing tests 1 hour before the deadline, it's gonna be terrible. First, you're not gonna like it. Second, you will get all the inconvenience of writing tests being tedious and absolutely no advantage while developing the project, because the tests are here to help you know when you're breaking something. So if you just put your test at the end, you can't break anything because, well, you've done all the code. So that's not helping you. And if you're writing code, writing tests just to make your instructor happy, you're really missing the point. It's to make yourself happy. You're here to kind of like help yourself, invest in your code base, and be sure that I can work. I can do this crazy refactoring. I can try this crazy feature because I have all the tooling that are fine. I have my test, I have my Git. So I'm going to branch, try something. If it works, fine, I'm merging back. If it doesn't work, and I know it doesn't work because I'm breaking all the tests or I'm unable to implement the refactoring or whatever, I just forget about the branch and revert to my previous save. And that's fine. Worst case, I've lost an hour, but nothing's broken in my system. So really, there's two things: the ability to record the system, branch to something else, start working on it, and if it doesn't work, you can just revert. That's really helpful. And if you couple this to testing, that gives you the most confidence you can have while you're developing. The ultimate confidence would be proof, but that's another debate. Here, we're like, I know what I can do, so I can try to do something else. And if while adding that feature, I broke something, well, I know it. And because I'm confident that my test suite is good. Assumption here, your test suite is good. We'll see this in the last section of the course. So that was when I had access to source code. But also something that we can do is actually consider the source code as a black box. Oh yeah, it's pretty early morning, so t-shirt saying that I need coffee and coffee. Cheers, guys. So black box testing, in that case, I will assume maybe I can see the code because I'm the one who wrote it, or that's someone of my teammates, or it is available in my Git repository or whatever. But I'm having an assumption here. I can't see the code, or I don't want to see the code. What the benefit of this is that that can help me find the right test better, because all I can see is the MIS or the public interface, public method, maybe a real interface like we discussed in the previous course. So I just know what services are offered by the code, and that's it. How it's implemented, not my problem. I don't know. I don't care. So that can help us to be like, oh, what should we test? We can take the business logic, the business specification, and we can take the interface and can be like, okay, this is my business specification. So my customer, they need to be able to do this and this and this and this. This is my public interface. Can I check that my customer can do X by calling the public interface? And by doing this, that gives you two things. If you can, fine, write a test. That's a translation from your specification to what your interface is doing. Second point, if you can't, like there is no way for you to validate that something went good, went right for your excellent customer, maybe your interface is wrong because it means that the feature is not visible. There is no way to observe that the system did what the customer is expected because you can't check that value. And this is your second cross-check. First one is that we discussed in the last lecture. I have my business specification. I can derive a test case and I can use this to know when the feature is done. That's my definition of done. Okay, when all the tests related to that feature are green, I'm done. No need to continue coding. And this is exactly the opposite, but also the dual of this idea, which is, well, if I can't test it, it means that my customer will not see it. So option A, it's a wrong test because that's not what you need. Option B, it's a wrong interface. Your interface, your MIS, your public method, whatever, does not do the right thing. Maybe the method is printing the result instead of returning it. And if you want to test, you need a return. You don't need a print. Because remember, we're not supposed to print. We're supposed to log at most, but we're exchanging data between objects. So we think of tutorial number 2, which was the elephant carpaccio, where you were doing this stuff to sell merch from McMaster Bookshop. And basically the question is, okay, I have a system that prints invoices and bill customer. What should I test? put the video on pause, do some things for like a minute, and then you can restart the video. Well, what I want to test is stuff like maybe the date. There's a legal requirement that is on an invoice. I need to have the date, which is today's date. I can't post a pre-invoice. That the price is correct, number, amount of items, tax applied the right way, the right tax for the right province, all those kind of things. That can looks like a good space of element that I want to test. And this is actually something that I can do. This is not formal yet, okay? Just like I have my business specification and I want to look at what to test. If I do have something more formal being an MIS, an ADT, or just a simple interface or public method listed for a class or header file in C or those kind of things. We can actually go a little bit more in details of what we can test because that gives me information, okay? I'm having like a point, the notion of point as an MIS with an X coordinate and a Y coordinate, and I have this function I can use to compute the distance between elements. So if I want to test element about a point, I can actually not look at the code. I don't care how the point is represented in memory. I just know it's public interface, which is I can create a point that takes one real and another real number, the output to the point that the constructor, and if there's a problem, I will get an invalid point exception. And out of this single line, I can actually derive 1, 2, 3, 4, 5, 6 test cases. I can test the new and then getting X. I can test the new and getting Y, so the value are right. And that's the kind of error that usually happen when you're giving like two coordinates in an array, maybe a map, maybe an island map that you're trying to explore or create in the context of your assignment. Is the first one the eighth and the second one the width, or the other way around? Subtle bug, but that actually transposed your representation of the world. So I want to be sure that X is X and Y is Y. What happens if X is negative? What happens if Y is negative? What happens if X is too big? What happens if Y is too big? Well, that should throw those kind of exceptions, right? And for the distance, same thing. I can have like a distance, take another point, it gives me a real number, fine. What I can compute the distance between 2 points, okay. What the distance be 0, what the distance being the maximal distance I can have on my map, what the distance being between me and the border, what like on the X side, and what's the distance between me and the border, like projection on the Y side. You get the point? So this design slash blueprint slash reflection slash you can't wing it approach, that's everything is connected. We're capturing the business specification, which are vague and imprecise, but requirements engineering next year will be even worse in terms of vagueness and imprecision because that's the ordeal of software engineers. Then now that we have stuff that we can work with, we can refine those into actionable artifacts, being MIS, being ADT, being interface, being whatever. And this brings us to the point that this actually helps us knowing what to test. And because we know what to test, we can write tests that gives us the confidence to continue working on it. Use this notion of like, everything's connected. So far, you are looking like, oh, I have the MIS, I have the code, I have the solid principle, I have the grasp, but that might look like a constellation. But actually, we're really having links between all those concepts and this because everything's holds together that we can call this software engineering. And this is how we engineer software. We basically built like a layer, a foundational layer of things that help us building software, dealing with the fact that software is soft. But something important here is that we all know that we're not going to have an MIS or an ADT or a very specifically described, extremely overly documented interface for each and every part of the code because we just can't afford it. Trade-off, we're going to do this for the most critical part. But for the rest, that might not happen because of budget time issue. So we do need guidelines. We need a way to navigate among all those being like, okay, am I doing whitebox testing? Am I doing Blackbox testing? Okay, then what to test? I can like select randomly, but that will not give me any confidence that I found the significant test cases, the significant cases, situation that are good for my system. So accumulated after years of experience, people started to be like, okay, this is not a kind of like this is not exhaustive, and it doesn't mean that you have to do everything each time, but usually when you're testing, you have to think of it from a bicep point of view, which is boundary inverse cross-check error performance. Okay? And if you cover this, well, that should be okay. Again, not a proof. Again, it depends. Again, you have to justify where you're doing things. But that can give you guidance like, oh, I should look at the boundary. I should look at the inverse. I should cross-check, those kind of things. So if you look at the boundary and we remember the square root stuff from last time we're like, oh, I have the square root, fine. Let's start simple. Square root of 9 is 3. I take a number, multiply it by itself. I take the square root of that result. I should go back to the number. Fine. That was kind of like an easy way to start understanding what the square root was. And that's like square root of 9 is 3, square root of 25 is 5. I mean, no need to be genius to get this. Something more complex. What the value of square root of 0? What the value of square root of infinity? And actually, infinity doesn't exist on the computer because square root of infinity is like defined mathematically point of view, at least in terms of order of magnitude, but infinity doesn't exist in Java. We have double dot max value. So can we actually compute this? Does it work? Can it fit in memory? Who knows? Maybe we have to test it. And third point, sorry. 42 is a universal answer in the universe. So what is square root of 42? Well, it's 6.4807406981. Fine. But what's our level of precision? I mean, floating numbers are pretty hard to ensure in terms of precision. You will see this in the architecture course, and I mean, floating number are evil. But is 648 equal to square root of 42? Maybe not, but how many significant digits am I accepting for my computation of square roots as being the right result? That's something that we need to test to be able to know that we're good enough at a given level of precision. The inverse relationship is something that you can actually test when you know that you have a way to go back to the original state when you're doing something. So the main example is this square root thingy, for example. I have a number multiplied by itself, and if I take the square root of this, I should go back to my number. So whatever x is, this is the first line. If I multiply x, takes the square root, I'm back to x. Considering given like significance in terms of floating number. But that being said, this is something that I need to ensure. This is one of kind of like a property ensured by the definition of square root. Second example, if a divided by b is q, then a should be b times q. Okay, that's the kind of thing that you can have. In the context of software, we often don't have equation. Okay, that happens in scientific computing, that happens in like computer visions kind of things, which is perfectly fine. But if you're thinking of like have a website that sells products, I don't use square roots usually. But that doesn't mean that you don't have any inverse relationship or you don't have any property. Okay, because a property is just like a Boolean function that you can apply to your objects. And in your website, well, your product, your customer, your whatever, they're abstractions. They're stuff, they're first-class citizen. So for example, if I take data, I put it in the database, well, my inverse relationship is that if I look for it, I should be able to find it. So that's the kind of things, sorry, that you can think of. Okay, if I'm doing something and I have a way to come back, I need to check this. This is not just about doing something, that's the first level of testing. It's also being able to come back. So this is the example, still at test annotation, this is a test, hey GUnit, deal with it. I have my context, which is x being the square root of 25, and I'm asserting that 25.0 is equals to x times x. And I will check this with a given level of precision being 1, 2, 3, 4 significant digits. Okay, so I'm not really testing, and I can do this with actually any value. But what I'm interested here is that I don't know x, and I don't want to know x. But if I multiply x by x, I'm equal to 25, and that's fine. That means that my square root function is good. Second point, the C of bicep is for cross-check. So cross-checking means that I have something else that can compute the same result. And I want to be sure that my new stuff works the right way. Example of this could be you have a square root, which might be expensive to compute, who knows, or you can imagine you have something which is expensive to compute. And you know that in your specific situation, you can apply some heuristics and you can compute it way faster, but just for this specific context. So you can't replace the slow or expensive method that works in the general case with your new amazing method. That just doesn't work because this method only works for a very specific subset. But what you want to do is cross-checking that the very slow method and your very optimized method produce the same results. Because if not, your result is wrong. Think in terms of assignments. Assignment number 1, you were finding a maze, a pass inside a maze, fine. And then you were able to factorize the pass, or you were able to compute the pass in a different way by using the Tremo algorithm. This is a way to cross-check. You have your base canonical minimal viable product, which is I always follow the right wall, and at the end I get like a complete pass. And then I want to compute the pass in a different way, and I want to check that the result is the same, or that I end up at the same location, so I can verify the pass. And this can be done very different way. Like if I want the number of students, I can count the number of students in the database enrolled into AA4, and I can also take the number of enrolled and the number of withdrawn, and that should give me the current number of students in Avenue, okay? Because Mosaic contains the enrolled and the withdrawn, and Avenue only contains the number of students. So I can combine those different data to actually cross-check that the synchronization between Avenue and Mosaic is right. You should kind of like be, what the hell is he saying? Because I'm just saying in terms of number here. I take the number of students in Avenue gives me 150. I take the enrolled in Mosaic, that gives me 156, and the withdrawn, that gives me 1. So yeah, 155 is equals to 156 minus 1. But this kind of test, this kind of cross-check doesn't cross-check that it's exactly the same students. Okay, maybe there's an error in the enrolled and the withdrawn that happens to be okay from my testing point of view. You get the idea? So the whole point is really finding what makes sense to test and to what extent you need to go in this cross-check. Do I need to cross-check that each and every student in the list is enrolled? Maybe, maybe not. Maybe I just want to just check if there's discrepancies or stuff like this. And I can actually accept that, oh, maybe there will be an off by 1 error. That's fine. I'm not grading. I'm just listing students on Avenue. So that's okay. If I was grading, like giving the grade, entering the grade that goes to a transcript, then in that case, I want to be extremely sure that all the students are the right ones. So I need to have this cross-check mechanism, a way finer grained, way more refined to be sure that all my students are the right ones. Okay? So those cross-check, really important when you have several systems that are working together, several way of doing the same thing. You want to be sure that the result is equivalent, even if the method is different. Which is what we're doing with interfaces. We're implementing the interfaces in a different way. So we basically want to be able to cross-check, and that's what interfaces, abstraction shield, whatever you want to call it, help you to do that. I have several implementation of my interface. Fine, I can use one implementation to check the other one. Third point, the E of bicep is error. And the notion of error is that it's gonna happen. You're not living in a world which is ideal, where everything is perfect, everything is adapted to your software, and that is so cool that you're living like surrounded by butterflies and um, divine lights around you. That's just not the case. Life sucks, and it's gonna go wrong. So failure gonna happen, usually at boundaries, but failure can happen anytime. And especially so far, you're just working on your computer. But when you look at distributed systems where one system needs to call to another one that go through the network, everything can go wrong. You can lose the network. Someone can cut a cable at some point by accident in construction work, stuff like that. So really, when we're testing software, we should assume that life sucks. You want to write file, and there's no space on the disk. You want to query a remote server, the network's down. Or this one is pretty interesting. Tesla, they had this amazing key on your phone, and basically there's a guy who almost died because of this, because he stopped in the middle of the desert just to go for a quick break, and the car locked because that was a longer break than expected. But because there was no access to the 5G network, well, the guy was not able to open his car because the phone to connect to the car need to go through the network. So, and they were in a dead zone for cell phones. So that's the kind of things that might happen because, well, you're like, oh yeah, we're always connected, that's fine. And then suddenly you're running a mobile application and suddenly you're in the middle of Coot's paradise and you have no cell network. Okay, what's happening? Maybe it's a problem, maybe it's not, but you need to think of it. And the last one is the notion of performance. So 2 3, you're thinking in terms of theoretical performance. 3xb3, you will experiment with it about benchmarking and stuff like that. Um, what you want to be sure is that is your order of magnitude correct? You don't want to say this answers in 2.23 seconds because measuring time, it's a mess. What you want to know is that if we're thinking in terms of sorting algorithm, and that's something you will see in 203, you know that there are several ways of sorting and they have several order of magnitude. Insertion sort is n squared, quick sort is n log n, and radix is n. So what you want to know is that, okay, if I have an element of 10,000, insert 10,000 elements in my array, insertion sort should be slower than quicksort. If not, it means that my quicksort is bad because that theory tells me that quicksort should go faster than its insertion sort. And that the kind of things that for 2AA4 performance testing in an entire realm, there's crazy research activity on this. So it's not just like reduced to this, but for the sake of conciseness and introduction, when you're thinking in terms of performance, just think of order of magnitude for 2A4. I had some discussion with some of you during the first assignment. We're like, oh, I need to extend the size, like I need to use that flag to give Java more memory to explore a maze. And you're like, no, that there's a problem in your algorithm if you're doing this, because you should be able to escape a maze following the right wall basically quite quickly and even on a big maze. So that helps you knowing, thinking in terms of what the performance of the code, what the execution of the code, that gives you this. And this is also related, everything is connected, to the course where we discuss development and operation. Okay, I should know the operational context, so-called DevOps, of how my system is executed. Because if I need so many memory and I'm running in a microcontroller that doesn't have that memory, if I'm working on data that are so big that suddenly I need to configure the JVM in a different way to be able to absorb all those data in memory, then I need to know it and I need to test that it works at scale. Finally, for the last 10 slides, we're going to focus on the thing that is usually the most important when testing. This is not general case. And actually, there's other things that are important for testing. But when you're starting testing, because you don't know what you're doing, that's a good way to be sure that you're doing something that has value. Okay, there may be other stuff that are value otherwhere, but maybe you're not experienced enough to kind of like find them easily. So focusing on B from biceps, boundary, and then in the context of boundary testing, we're going to look at this and we're going to think of those. That's a good way to just not fall off the cliff. Okay, like maybe it's not the most the fastest path ever to the best test suite that you can define, but that's kind of like something that you can use as a checklist. Okay, I'm focusing on boundary and I'm going to correct, and by this I should be okay, because boundary unit tests are the most important one among the most important ones. That's really something important. So conformance. Um, if you consider just a simple email address, so that's my email, motors at macmaster.ca, what would be the boundary condition here? What would be the border of the space of what a correct email is, what a conform email is? Well, what if I meet the at symbol, master s, macmaster.ca? What if I'm missing the .ca? What if I'm missing the Mac ID? What if I'm using spaces, using special symbols? Can I use a plus in email? Well, actually, yes, you can. The specification of how you can write an email address, it's defined by what's called an RFC, and it's really long. It's really complex to actually define an email address. So the whole point here is not necessarily to be exhaustive, but being like, oh, I have a field on my website where people will enter their email. Fine, I should test how my system will react if those data are corrupted or not a good one. So it's not about preventing user to enter those. That would be defensive programming. That's a different topic. Is getting confidence that if by any mean you receive an email address without an @ you will consider that there's a problem and you will not just silently ignore it. Okay, so that's the whole point. In this non-conform situation, how should my code react? The O of correct is related to ordering. Okay, and that's an extract from this really great book, which is Pragmatic Unit Testing in Java with JUnit. If you're interested in testing, really read it. It's quite easy to find it, and I even think it's at the library. And honestly, that's one of the best introduction to testing book from a very pragmatic coding point of view. So if you like coding and if you're interested in testing, that's my go-to book. So you're at a restaurant, fine, and you're kind of like ordering food, fine. I can actually order food in any order. Okay, so, oh, I will have this for dessert, and I will have this for as the starter, and I will have like the salad and stuff like that. Um, this is the role of your waiter to actually take this, like go through the conversation with all the patron at the table and record everything, knowing who's ordered what, blah, blah, blah. And adding my elements on the, when they go to the place where the waiter can enter the elements on the bill system. So it goes to the kitchen and so goes to your bill. They're entering the stuff like new guest and this is blah, blah, blah. I can do this in any order because, well, guests are stupid, right? We all did that. We order something and then the waiter come back and say, oh, by the way, I might want to change this. Or, oh, by the way, I would like to add this. So the order needs, by business logic specification, to be any kind of order. Okay, I can start with the dessert and then go to the entree or the starter and then add a salad or whatever. But when I'm getting my order out for the kitchen, we need to do some scheduling because I should not start preparing the desserts if I haven't even started my starter. So the iterator, the way that I'm extracting information from the order, should be first the salad, which is the starter, then the entree, and then the dessert. So there's typo here. And this is actually giving me that property of ordering. I need to be sure that my order is correct. And that's something you might experiment in your assignments. Maybe before taking the decision of turning left or turning right, I need to know my surrounding. So I need to have checked my surrounding before being allowed to turn, because if not, I might get lost. Notion of range, that's something that you more or less experimented before, but that's going to be like more and more. The more complex the data structure you're working on, the more complex the problem you're working on, the more range problem you will have. Can I draw a card from an empty deck? Can I add more than maximum number of cards to a deck? Can I remove -4 cards? What does that mean to remove a negative number of cards? All those kind of things we need to check. We need to know when we're working with a set of elements, a collection of elements, a list of sequence of elements, whatever, we need to check what's happening. Like what can happen if we give you stupid input. And this is not exhaustive, but something that you can do is check the number of elements. Okay, you have an array, fine. You have 12 elements, but you have 15 slots in your array. That's weird. There's something weird in between. You're not seeing all the stuff. Is the first index greater than the last index? That's pretty weird. Is your position negative, meaning like you're like going backward? Is that even allowed in the system? Is the current index greater than the last one so that you're actually going in the right direction? All those kind of things. There is no immediate answer for all of those questions. That's the kind of thing you can ask yourself when you're working on the collection. Okay, is my stuff going in the right direction? Do I have enough elements? Am I going out of range? All those kind of things. The second R of correct is reference. Notion of reference is, well, the way I can work with my system depends on its state, okay? Encapsulation, information hiding, have some data that are hidden inside my object, and the object will not react the same way when I'm sending message, when I'm calling methods, depending on the content of its attributes. Take your car. If I'm in park mode, I can't accelerate. I can't draw a card from an empty deck. Okay, the deck is empty, this is encapsulated, so if I draw a card, that will be an error. So that gives me kind of like precondition and postcondition that needs to be tested. The car needs to be in drive mode to be able to trigger the acceleration. So if it's not, that should be an error, and you should receive a message on the dashboard saying, hey, dude, you can't really accelerate because the car is still in parking mode. Not last actually, second to last is the notion of existence. Well, third to last actually, there's two left. The notion of existence is, we talked a lot about so you can't draw a card from the empty deck. Fine, but can you define it? What do you get? You get an empty card deck exception. Your computer bursts into flames. You get null. You get optional.empty. You get false. Like what the result of this? And you need to document this at some point, and documenting it as a test is a good way to ensure that your design decision, and we'll talk about the notion of absence of value, which is this kind of situation in the next lecture. You're taking a design decision here. There are different ways of doing this, and document it as a test. That's a good way to kind of like be sure that this design decision will stay the way it is. And so that works for the stuff you've defined. That also works for the stuff that are coming from the environment. Remember, failure is going to happen. You will try to open the file and the file will not be here. You will try to contact the network and the network will not be available, or the server in front will take so much time, so long time to answer that you're just like, okay, I should stop it. When I started at Mac, they didn't give me an office because I was working remotely for the first 4 months. And that actually triggered an issue with the parking system. When I started working physically here, my parking transponder was deactivated each Monday morning. That was pretty weird. And after a month of having to call the parking service each Monday morning, we realized that my Mosaic profile doesn't have an office number, which was not okay for a prof. So when this data was synchronized with the parking system, say, hey, he's a prof, he has a transponder, and this is took out of his salary. Basically, there was like a mismatch because a prof is supposed to have an office number, and bam, the system on the parking part was like, ooh, inconsistent. I'm killing that guy. It doesn't exist anymore. So that was exactly an existence problem. Second to last, cardinality. Notion of cardinality is kind of things that I was talking a lot about the array, because that the immediate one, basically thinking in terms of going really to the essence of boundary, 0, 1, and rule. I can handle no objects. I can handle the first element and I can handle more than one. If I can do this, there's no need to test 5, 10, 15, 16, blah, blah. I can handle 0, I can handle 1, and I can handle more than one. That is pretty fine. Second point can also be notion of like computing the number of elements you're expecting. You've 12 feet of lawn and you want to put a fence with 3 feet wide between the different fencing section. How many fence posts do you need? Well, it's not 12 times 3, it's +1. So that the kind of things like be sure that your expectation is right, because it's always those off by 1 that might be an issue. Oops. And the last one is the time. Time is extremely difficult. Time is a pain to handle when we're developing software. And this has 2 dimensions. First dimension, time can be relative. Okay, so it's like I need to do stuff in a certain order. That's what we're saying in the order one. So I need to log in before logging out. I need to open the file, then I can read, then I flush it, then I can close, or then I write it, then I can flush, and then I can close. Okay, this is kind of like protocol situation. Second situation is the absolute time. And you have to deal with time zone, you have to deal with tons of stuff that are really annoying. Main example, if it's 1:45 a.m. and you add 30 minutes, 364 days a year, that gives you to 15 a.m. But if you do this during the DST shift, you're actually going backward, and it will be 1:15 a.m. Very corner case, but that's actually triggers some issues. To conclude, so we've seen the importance of tests on the previous lecture. This lecture was about you can do tests in the Whitebox way, in the Blackbox way. Whitebox, because you know the structure of the code, you can try to minimize the test case to maximize the coverage, whatever coverage you're targeting, being instruction, branch, edges, those kind of things. And Blackbox is like, nah, I just have the specification, and I'm kind of like conjuring only that specification. Because the test case space is so big and so large, you need guidance. And guidance comes with BICEP and correct, 2 acronyms that need to be known at some point that helps you really finding the right stuff. Those are common sense. Looking at the boundaries, looking at the conformance, looking at the performance, looking at the timing, looking at the range, all those kind of things like, okay, I need to, it goes without saying, right? But it's better when it's said. So if you focus on this, that should be fine. So thinking of your assignment, that's what you're doing in this week tutorial. You will think of your assignment in terms of BICEP and in terms of correct, not writing tests. That's a demo from TA, which is about writing tests. But it's more like think of what you need to test. That will be all for me for this video. There is one remaining video lecture for this week, which will be an example of how to handle design decisions such as there's no value here. I can't pick a card from an empty deck. What should I do with this? Well, we'll see in the next video. So thank you very much and see you soon.